So 20% farmer and 10% farmer.
So I think we can get started. I just wanted to check. Can you on Team hear me and see the slides? I will assume that you can. Okay, so my name is Lorenzo Versini. I am a final year physics student, and today we're going to see convolutional neural networks. So it's going to be quite chill, so now feel free to interrupt me if you had any question at any time. Cool. So we saw last time, I don't know how many of you were at the workshop, I think some of you were, but we saw last time that we could use neural networks to classify images. So we had these 28 by 28 images representing pieces of clothes, for instance, a boot or a glove or a t-shirt. And we built a neural network that was able to classify with a decent accuracy what these objects were, right? Convolutional neural networks are used for image classification as well. So we might wonder, why do we need to do something different, right? Before even introducing what convolutional neural networks are, why can't we just use neural networks? So let's say that we have this task, right? We have this big picture, and somewhere in the picture we have an apple. And the task is recognizing whether this image contains an apple or it doesn't. So this is what we did last time. We took this picture and we split all the columns. Then we took all these columns and we stacked them together here at the bottom in this way. So we basically flattened a two-dimensional image into a one-dimensional row of pixel values. What we did then was taking all these pixels and considering them as our input. So each of these pixels is a feature, and we connect them to, I just put one layer here, but ideally we connected them to many layers. And at the end, we may have, for instance, one single neuron, and that single neuron could be 1 if there is an apple in the picture, or it could be 0 if there is no apple in the picture. Okay. So can you see any issue in this approach? There are at least two problems with this. Yes?
Not running a projection. I think for neural networks, we project one thing, and then so basically that doesn't give you enough information.
Okay, no, yeah, it's a good guess. So it's kind of what do you mean? Well, it doesn't give a lot of information? Because it kind of worked last time, right? So we actually did this process, right? We had 28 by 28 images, and we did flatten them and connect them through some layers, and we did get the results that we wanted. So it kind of worked, right? Well, there are a couple of issues. The first issue is that last time we had 28 by 28 images, right? How big is an image usually, for instance, from a camera? It could be, yes, maybe 3,000 by 3,000 pixels. Okay, yeah, that's the standard. So we may have a 3,000 by 3,000 pictures, and you can do the calculation. This array here will already be huge, right? There's another issue. What happened to our apple? Our apple is scattered across all this vector, right? So we're kind of losing all the spatial correlation of the single pixels. So again, this is now, for example, for 128 by 128 pixel image, we're going to have this number of pixels, and then we're going to connect it maybe to 6 units in the first layer, and that's going to give us like at least 98,000 parameters that we need to tune, because each of these lines that connect a pixel to a neuron here, it's a weight, it's a parameter that we need to tune. And the other issue is that we lose spatial correlation, right? So this point and this point kind of are correlated the same way than this point and this point, right? Because they all get mixed up. Whereas if I know, if I'm looking for an apple somewhere, and I know I'm checking this pixel, I shouldn't look at this pixel, right? Because obviously I kind of have I expect an apple to be kind of this large. So what's the point of comparing this pixel and this pixel to check if an apple is in the image? So having said so, this is not what we want to do practically. And what we want to do is this one. Now this looks scary, it looks big, and we're going to kind of analyze each piece of this diagram in the following slides. So we start with an image, which as you can see that it has 3 layers, and this kind of shows that the image might have 3 colors, right? RGB. And then we have these kind of boxes here, a series of boxes. And now this is basically all today's lecture is going to be about, how to build these boxes, what these boxes are. And lastly, we're going to have something that's kind of more familiar. This is a standard neural network, a standard classifier, like the ones that we saw last time. So let's see the convolutional neural network approach. Yeah, this is just to reiterate, no, this is not good. Okay, so we start by taking our image of the apple and selecting a patch of 4 by 4 pixels, okay? And we create a neuron. We put this neuron in front of our image, and we start connecting each pixel to this neuron. So I'm connecting 1 pixel, 2 pixels, until I connect all the pixels, okay? Now this is kind of similar to our previous case of neural networks. Each connection carries a weight. And what I do is that I take the value of the pixel. So here the pixel is going to have a high value, right? Because it's the center of the apple. Here probably it's going to be about 0. I take the value of the pixel and I weight it by one number. For instance, here I have 0.1, -2, 0.7. And these values are tunable and are the things that we train for the convolutional neural network. So I take basically, I multiply each pixel by this value, and I sum the result of this multiplication, okay? So next thing, I take this patch and I slide it somewhere else, okay? And I repeat the same process. I compute the value of this pixel by taking a weighted sum of the values of this kind of the pixels in this patch that I selected. Now I'm going to move across all the image, not just horizontally. I'm also going to go vertically until at the end, I'm going to cover the whole image. So you see, by doing this process, I'm building a sequence, kind of a grid of neurons at the end, right? And these neurons are basically going to be my new picture. And I can apply this process over and over and over. Now you may be concerned by the fact that this was 8 by 8, and this is 5 by 5, right? So it kind of shrunk down. This is not too much of a concern, okay? There are ways to kind of get around these issues of the image that shrinks down. So no, it's okay. If you want to keep the image the same size, you can absolutely do it. And this process of sliding this window and calculating the value of these neurons is called convolution, okay? So I'm going now to show a recap of the convolution. So here's what we did. We started with an image. Yes?
The value of the apple based on the pixel color.
Yeah, so this was kind of a stupid example. So the image I would have in this case is that because obviously now this is a pixel. I cannot have a pixel now, a leaf in a pixel, right?
Also just like a 1 or 0.
Yeah, it's going to be 0, 1, right? And possibly all the values in between. So, because an image has kind of grayscale, right?
Oh, yeah.
It's not black and white. You have areas that are more gray, darker and lighter areas. 2 questions. Yes?
What is each weight of each? Like how likely the things that an apple can have pixel? What is it?
Okay, it's an excellent question. So you can think it this way. So imagine that these pixels here, okay, all these values, if you printed them with your printer, you would get an image of an apple. Okay, so let's say that, let me go here. So this is basically our whole image, and I choose these values carefully so that they represent an apple. Okay, then you can check, with pen and paper, but if I superimpose this patch where the apple is, I'm going to get a value that is high. Okay, if I put it here where everything is 0, I'm probably going to get a value that is quite low. Okay, so these things, they have the purpose of making some features more visible. So I'm actually going to give some examples of this, of these things, okay, in a bit. So if you want, I can ask you again after I go through the slide. You can tell me if it's still not clear. You had a question?
Yeah. How do you deal with, say, you've got apple overlaps with the side of the unit? So the sliding window starting just from the corner, but if you've only got, say, half an apple and half it, then surely the window approach will capture that.
At this point, I think it would depend on your training data, right? So if you show your computer many pictures of apples, cut apples, right? Then you will kind of learn to recognize an apple maybe just by the shape of the bottom part, right? Or by the colors, maybe, or just by the shape of this part, top part here, right? So yeah, kind of if you have a well-trained algorithm, it's probably going to be able to detect things that are cut off.
Would the same go with
Yes.
That's what they say.
Yes, true. So if I show the computer only apples that have the same amount, they occupy the same amount of pixels, it's very likely they wouldn't recognize a bigger apple. But this is kind of easy to solve, right? Because I can take my initial data set and I can maybe zoom on the apples, right? And I can rescale the image. So I'm going to have, basically, this is called data augmentation. So I start from a set of data and I'm thinking, well, this is not general enough. This is maybe not enough data. So I can do all these transformations that produce images that are still, let's say, likely to happen in real life, right? And this way my computer can learn to recognize bigger apples, smaller apples, and so on. Okay, so let's do a recap. So I understand this is still a bit mysterious, this thing here, but we're going to go through it. So this process of sliding this set of values is called convolution. Sometimes mathematicians, they symbolize it with these asterisks here. Okay, so I would say that this result, this matrix here, is equal to the initial image convolved with this set of values here. And this image is taken from towards data science, and it kind of shows what we're doing, right? So we're taking a patch and we're projecting it into this other new image here. Okay, this thing here is called kernel. And we're not changing the kernel, we're just changing the patch that we're considering, okay? So this set of values stays the same as I slide this window and calculate all these values. Lastly, in the case of neural networks, we use activation functions, which kind of have the purpose of breaking linearity. So if you don't use any activation functions, okay, having 10 layers, having 2 layers is the same thing, basically. So we need an activation function, kind of give a purpose to have more than 1 layer. Okay, and same thing we're going to do. So once we compute this multiplication, we sum all the values, we're going to put them into some function. For instance, it could be a sigmoid, it could be rectifier linear unit, which is another standard activation function. Now let's get to the kernel. Okay. So let's say here I plotted an image, there is a circle. Now, a circle, an image has some pixels, and now the pixels can have some values. Here I chose pixels that had values 0 and 100, right? So it's kind of, I made it three-dimensional so that all these pixels have value 0 and all these pixels have value 100, so they're kind of higher, right? That's basically a picture. Now, let's say they would choose this kernel. This kernel is a Gaussian, okay? So a Gaussian is kind of a blob in 2 dimensions. So you could see it as yeah, it's kind of how you kind of have this, if you imagine this landscape, and then you have a hill, that hill would be your Gaussian, right? And when I slide this Gaussian over this circle, what I'm doing is basically spreading the pixels around, okay? So by doing this process, I transformed this image to this kind of hill, okay? It's smoother. If you see that the change from white to black is less neat, and I have this kind of gradual sliding down, okay? Now, let's see this other example. So this matrix, which is a 3x3 matrix, is sometimes used for edge detection, okay? So see what happens after I pass it to this circle. So first of all, the center of the circle is at 0 now, okay? Which is quite impressive, right? Because before it was 100. The outside of the circle is 0. But what's happening at the edge of the circle? An idea? Yes? Yes. We're getting very high and very low values, if you see. There's kind of a very sharp oscillation at the edge. Okay. So if I plotted this image, I will now get a ring. Okay. So choosing different kernels, these things are called kernels, okay, they allow to kind of transform the image in ways that may be useful. So in particular, this process allows us to find edges, sharp edges of things. So now, one of the tasks that convolutional networks are used for is called image segmentation. And in image segmentation, we start with an image, maybe a chair, a table. What we try to do is find the perimeter of the chair, the perimeter of the table, and kind of distinguish all the objects, okay? So in this case, this kernel would be very useful. But what is extraordinary about convolutional neural networks is that we don't have to choose the kernel by hand. The computer is going to choose the kernel that is best suited for what it's trying to do, okay? So you give the computer images and the task. The task is predict, if there is an apple in this image. And the computer is going to try and tweak different kernels in order to try and recognize apples in the image. It's kind of more powerful than doing it ourselves. We can do it ourselves and still get decent results, but it's definitely better if we can to let the computer do it by itself. Is it kind of clearer? Okay.
The product with the color what's the product?
Sorry, can you repeat?
You know how in the window sliding you're finding the product or the convolution with the kernel and the image? And is the image the color of the pixels?
Excellent question. So the example I was having before, it was kind of a toy example. So the image was black and white. For an image that is black and white, I only have pixels with value from 0 to, I don't know, something, 0 to 1, 0 to 255. If I understand your question properly, you're asking, basically the question is what happens when the image has colors? Yeah. Maybe what are the question?
Yeah, basically. So it's the product from the kernel to the, you know how you find like this kernel product or this convolutional product, right?
Yes.
What's the number, what numbers are you taking from the image represented?
Yes.
Is it the color?
So if in a black and white image, I take how dark or light the image is, okay? So when you take a digital image, it already does it for you. So it maps kind of the signal on the sensor to a range of values. That's the value I'm going to take, right? You can try and open an image in Python, for instance. You can see that all that it is just a sequence of values between 0 and 255. Okay. Things get tricky when you have colors. So your image then is going to be 3 matrices of values from 0 to 255, each one representing one of the colors. I still think that maybe I missed your question. So if you want, you can come. Oh, got it. Okay. Amazing. So this is the process we're doing. And the idea is that we let the computer choose. Okay, this kernel means nothing. I just picked the values random. But basically, we let the computer choose in the right kernel to perform a certain task. So this is what happens when we have colors in our input image. Instead of a matrix, I'm going to have 3 matrices stuck together. Each of these boxes is a pixel, okay, in our image. And what we do with the convolution is, so before we had a grid, for instance, a grid 3 by 3 of values. And now we're going to have a cube. Our kernel is going to be a cube of values, okay? And we connect all these orange cubes to this new neuron, okay, like this. And we compute the value as previously. So we take the value of the pixels in the blue, for instance, we time it by some weight, and we sum it in here. We do the same, for instance, for this pixel in the red layer. We time it by some weight, and we sum it here, okay? And we slide this block, like in this, using this approach, and we get to scan the whole image. Now, the thing is that we saw before that now we had one kernel that kind of smoothed out images. We had one kernel that kind of did some sort of edge detection, it looked like. But what if we need more things, right? What if in order to detect an apple, we first need to kind of smooth some noise, we also need to do some edge detection, we also need to look for some particular detail of the apple. So in that case, then we want to use more kernels, okay? So the way we're going to do this is basically choosing multiple set of values, okay? So we're going to pick multiple of these things. And once we perform a convolution, we choose, for instance, the yellow kernel, and we build a new image in front of it using the approach. Then we take the green kernel and we do the same thing, and we build a new image that we stack on top of the yellow. Then we choose another set of values, the blue values. I'm going to perform the convolution. I'm going to get an output image, and I'm going to stack it on top of here, right? And I can do this many times. All these new layers that I'm creating are called channels, okay? So when you hear talking about channels in convolutional neural networks, it means this. So if I have like 8 channels after the first image, it means that I chose 8 kernels to train in order to extract some useful information out of the image. Okay, this is because the more the merrier. So adding more things means that I can detect more details of the image. I can tweak the kernels to work together, maybe. So let's see some terminology that is usually used with convolutional neural networks, and it's particularly useful if you're trying to implement them in TensorFlow, for instance. So the stride is how much I slide the window. Okay, so let's say that your initial window is this one right here. So if the next window is going to be here, then I did 1, 2 jumps, okay? The 2 jumps are called stride plus 2. Then our kernel is going to have a height and a width. In this case, it's 3 by 3. In this case, it's 2 by 2. Okay, so the thing that we're seeing here is a convolution with stride plus 2, height 2, width 2. So we said before that we noticed before that the image shrunk down. Okay, I started with an image that was, I think it was 8 by 8, and I ended up with something that was 5 by 5. I don't remember, something like that. So one way to solve this is by adding padding. So I add extra pixels at the sides of the image. Okay, and how do I choose the values of these pixels? Well, I have many choices. So for instance, I can do some mirroring. So this pixel is going to be equal to this pixel. If I need to add more padding, this pixel is going to be equal to this pixel. So I'm taking the border and I'm making a mirrored copy of the image on the side. I can fill these pixels with a value that I can decide. So for instance, 0. I can fill this pixel with a value that is beside it. Now, so this pixel is going to get this value, this one is going to get this value, and so on. So now, plenty of ways. And remember, all these things, you don't have to implement any of these because it's all in the Python libraries, okay? So now we're kind of describing how this process works, but technically when you write and you code things down, it's much easier. You just tell the program, the function, the things that you want. For instance, you tell it, I want 8 channels, and it's going to create the kernels for you. You don't have to think about these things. Any questions so far? Yes.
Why do you typically like RGB?
So the question is for people on Teams. So the question is, why do we use red, green, blue to represent images instead of hue?
Yeah, so there's like the print ring they use colors to represent different numbers to represent colors.
Yes.
And then you also got hue, saturation, light.
Yes.
And why is it that red, green, standard?
Yes. So the question is, why is the red, green, and blue the standard for images? And no, some other ways of representing colors, they're maybe used by printers and so on. Answer is, I don't know. Sorry. I'm sure there's probably a reason, but I personally don't know. Maybe it has to do with the sensors, but I don't know. Yes?
How do we have to separate the two are red, green, blue instead of just making it as previous and just make it like 1 to 16 million?
1, 2?
Like, why do we have to separate it into RGB instead of just making a one number that represents all the possible colors?
One number that represents all possible colors.
Yeah, like maybe like 1 to 16 million.
Okay, so
Like how we did with the black and white images.
so for instance, if my colors can be from 0 to 1 with 10 separations, right? I will use 10 times 10 times 10 to have like possible combinations. So the thing is that, yeah, you can have different values of red, blue, and green for the same pixel, right?
Yeah.
And
Why do we have to separate them into RGB instead of one?
we don't separate them.
We separate them into like 3 times 3 times 3. Why not just make it like 3 times 9?
3 times 9. So you kind of want the idea. No, your picture is 2D, so you kind of want something that is 3 by 3 here, so that it slides around the image, right? So that's something you want to keep.
Yeah.
You want to keep the bidimensional concept in your convolution. So surely you need to have a 3 by 3, and then you do have you have 3 other layers. So you need to add. Now, your kernel needs also to combine these other pixels.
Okay.
You can have a convolution that is 3-dimensional.
Yeah.
So you slide this block basically also in the width.
Yeah.
So at this point, you could have maybe just one layer that goes in this direction, and goes kind of everywhere. But we're focusing on 2D now.
Okay.
Yes?
Just a quick question. Does the font size have to match basically the image dimensions? So like if it was 100 x 100 x 100, like a huge weird image, your kernel size has to match that.
So the question is, does the kernel size need to match
Or like
the image dimension?
Yeah, dimension, not necessarily like number of not necessarily size, but dimension.
Yes. So in this case, this image has 3 dimensions, right?
Something has like 18 numbers.
Yeah. I would kind of depends, right? At some point, it's up to you. It's kind of up to you to decide what's kind of how you want to move this kernel, depending on your data. But yes, for instance, I don't know, you could, I don't know, it kind of depends really. So if you could add a fourth dimension by considering the time. So maybe this is a video, right? So you have one image here at this time, you have another here at later time. So maybe you kind of want to consider them separately, right? Because maybe the apple is moving. So in that case, maybe it makes sense to use a kernel that is three-dimensional, whereas your data themselves are four-dimensional, right?
Yeah.
So I think it kind of depends. So did I answer your question? Because yes. Yes.
I think kernels that
Yes. So the question is, when I say kernel, basically the question is, when I say a kernel, what do I mean? I mean the set of values. For instance, this set of values here, where I then time by the pixels in the patch, and then I perform the sum. Yes. All clear so far? Okay. Also on Teams, if you have any question, feel free to ask. So we got kind of the first part of the of this diagram. Okay. So what we're doing here is that this is a kernel that I'm sliding through the image of this car, and we see a rectangle here, because surely we have a square, because that's the new image that we are projecting. And the reason why it's a rectangle is that we're using more than one kernel, so we have more channels. Okay. So that's why you see all these rectangular boxes. Now we got to pooling. So if you see this one and this one, what's happening? Is there a difference? So what could possibly be happening from here to here? Yes? Yeah, okay, so the idea is that maybe we could be taking just the maximum of the kernels that we use. And it's kind of this is kind of the right idea. And that the thing that you're talking about is called max pooling, right? Yes? Would it be the sum of all the kernels?
would it be the sum of
all the channels? You mean like? It's fine. It's okay. But thank you for yeah. Yes, exactly. So what's your name? So what Alex said is it the case that we want to do some sort of dimensionality reduction to kind of shrink down all this data that they are created? Yes, this is actually the case. So what we do now is called pooling. Pooling is a way to reduce, as you said, the dimensionality of our object, now this rectangle that we just created. And this means that we reduce the memory usage, we reduce the computational load overall, and reduce the number of parameters that we need to train. And in general, we are reducing overfitting. Okay, so it kind of has many good things. So let's say that this is one image that we have. Okay, so there are two main ways of doing it. One is max pooling. So from each of these four squares that you can see, we're going to take the maximum value. Okay. Another approach is average pooling. So what we do is we take the sum of all these values and we divide it by the number of pixels. So we're taking the average. And so we do this process to kind of reduce the size of our images. And max pooling is kind of more used, at least now according to some people. But with some people, I mean one of the books that Canton suggested in the I don't know if you saw the blog on the website. But yes, the reason of max pooling is that it kind of forces it picks the highest value, and that kind of has some implications on noise reduction. because you're kind of discarding things that maybe are not useful, and you're forcing the network to kind of not put. So I'm not entirely sure, but I think it does have to do with discarding some information that maybe are not that useful for the task. Okay. Cool. So pooling works quite similarly to convolutions. So we can use the same terminology, stride and Windows sliding, but pooling doesn't have a kernel. Okay. So because pooling is basically this box that moves, and you just take the highest value inside the box. Okay. And for instance, if we choose a pooling with a window of 2 by 2 and a stride of 2, what I'm doing is basically just halving the dimensions of the image, right? So this is what we're seeing in this case. Same terminology. And yeah, no kernel. So yes, pooling usually doesn't happen over the channels. So usually the kernel is one-dimensional. I perform, one-dimensional in the channel dimension. Okay, so I perform the pooling over each layer stacked of my image. Okay, so if I start with an image that has 64 channels, like here, after performing pooling, I'm still going to get an image which has 64 channels. Why? Because then I can perform another convolution that is going to kind of consider all the channels, right? Because the convolution, contrarily to the pooling, covers all the channels, as we saw before. Okay, so in particular here, we saw that the convolution covered all the depth of our image. Okay, so now we kind of know how this first bit works. So I have a convolution and I have some pooling here. Okay, and then I have some convolution, have some pooling. We're going to see later now how to choose now what parameters to pick for the convolution and the pooling. Okay, but now we kind of have this. You kind of get the gist that people usually do this alternation between convolutions and pooling to kind of extract the information that we gained out of convolution and to keep the number of parameters low. Lastly, what we're going to do is classification. Okay, so the idea of these kernels is that they help extracting important features in the image. And so maybe now if I'm trying to distinguish cats from cars, maybe the kernel is going to distinguish the kind of pattern of the hairs of a cat, for instance. Okay, and at some point, I want to take all this information that I extracted and plug them into a neural network to find the answer of my question. In this case, in this example, the question is identifying this as a car rather than a truck, a van, or a bicycle. Okay. And so what we're going to do is that, let's say that we ended up with a 3x3 image with 6 channels after doing all this shrinking and convolution, shrinking and convolution. What we do now is that we flatten this block into a sequence of neurons. I just drew 3 here, but there will actually be 54. Yeah. And then now we plug it into a simple neural network to do our classification. So cat, dog, car versus bicycle, and so on. And we would have our standard cost function at the end, the kind of first binary cross entropy that tells us if car or not car, for instance. And this way kind of tells us if our model is performing correctly. So it's kind of a lot of parameters that are going to get trained. We're going to have parameters in the convolution. We are not going to get any parameter in the pooling, not directly. And then we're going to have some parameters here in the neural network, the classifier. Okay, so we kind of use optimizers to find the optimal values of these parameters. But again, everything is implemented. It's kind of happens under the hood. So you don't actually find the parameters yourself. You let the program, for instance, all the functions implemented in TensorFlow to do this for you. Now, this is not what people usually would do. If you see in the literature and in some available algorithms. So let me get a pen. So you start with a convolution with a 3x3 kernel, and maybe this convolution is going to produce 32 channels. So now you start with an image here. It's like 3 channels. Then you do the convolution and you end up with an image that has 32 channels. 32. At this point, you want to do some dimensionality reduction. So you would do maybe some pooling, 2x2, stride 2, which means halving the size of the image. And once you have this new image, I'm just going to make it shorter to show that I trunked it. I'm going to perform another convolution. And as I halve the size of the image, I double the number of channels. Okay, so you kind of have this idea of this image that starts very flat and not many channels, but very large, and kind of gets shrunk down, and it gets longer in the channels dimension. So again, try the pooling, I'm performing pooling, and then I perform another convolution, and I double again the number of channels. At some point, I take this image and I flatten it, and I plug into a classifier if I want to do classification. Okay, it kind of depends on what you want to do, the exact approach that you're going to take. And yeah, so this is about it for convolutional neural networks. Questions?
What is like the number? Because then we shrink. When we do pooling, then we shrink the thing. So how are we done with the number of channels? Like we shrink like the image.
Yeah, good question. So if we go back here, okay, we have this scenario. This is my image, and I can choose a set of kernels. This set of kernels is going to be another cube, okay? A cube of values. Because it's going to be a cube and not just a square, because this image has more layers, more channels, let's say. So I slide this cube, and after sliding this cube, here I will get a square. Okay. Because this cube is going to go through all these values here. Maybe we can see this kind of thing here, right? Yeah, so if you think about adding some other things here, the concept is going to stay the same, right?
A lot.
You get a lot of squares. So yeah, but it's going to be one layer of squares, of tiny squares. Yes. The thing is that at this moment, I don't have any other layer of squares. In order to get a new layer of squares, what I do is that I choose a different set of values for this cubic kernel here. Maybe it's going to be the green one here. Okay, I'm going to slide this one. Now, when I perform pooling, so let's say that it's actually this case here, right? We have 4, basically, the output of this one is going to be these 4 images here. The yellow, the green, the blue, and the violet. When I perform pooling, I have the dimension of this object, but I just do it in the, let's say, in this direction, and this direction here. Okay. So you see each of these things is 4x4.
Yeah.
So I have.
So you go up and you go down, like when you do the pool. Like you slide it that way.
We still slide it, all the ways. But if you think about pulling like just halving the number of dimensions, okay, what I'm doing is that instead of 4 4x4 images here, that's a bit unfortunate that they are all 4s. I'm going to have 4 2x2 images here.
Yeah.
Yes. So the number of channels is 4. I still have 4. I still have a yellow, a green, a blue, and a violet image. But now they're going to be 2x2 instead of 4x4. Does it make sense?
Yes.
So this is what I mean with like the number. This is why the number of channels doesn't change, because I start with 4 channels and 4x4 images. I end up with 4 channels and 2x2 images, because Okay, maybe I was a bit quick in there. Yeah, I actually I said it.
Yeah.
So the number of channels doubles after I perform a new convolution.
So after the convolution, not good.
Yes, so after the pooling, same number of channels, half dimension.
Yes.
After convolution, same dimension, double number of channels.
Okay. Yeah, because I was reading this one.
Oh, they actually write something wrong.
So after each convolution, double the number of channels. Okay,
Oops, sorry.
sorry.
Yeah, this was.
Just got confused. Channels.
Thank you for spotting it. After each convolution.
Yeah.
B.
Yeah. Thank you.
No, thank you for noticing it. Wait, I think it was before.
Yeah, so that's doubling after convolution. That's because we choose that. So we choose to add in more channels.
So the question is basically, why do we double the number of channels? Now, do we choose it, or are we forced to double the number of channels? No, we're not forced. We can always choose the number of channels. I'm not entirely sure on why there is this factor of truth. But surely there is one fact that if you keep shrinking your image, you are going to lose information, right? So if you think about, now if you do a massive pooling where you shrink all your image on just one pixel, right? How can that pixel contain any information about where your cat is, right? So you kind of reduce the information by pooling, but then you want to extract some new information by adding more channels. So maybe I'm not sure if my answer is completely satisfactory. Probably I wouldn't be satisfied with my answer, but maybe you can give a look on internet. I'm sure you would find some justification of this.
That makes sense, but I guess why at the end then we use that layers rather than just using down on the channel for value there is a happening.
So it's a nice question. So I mean, in this particular case, if our convolution is a 3x3 kernel, we're basically doing what you're saying. Okay? Because we're not sliding anything. We're just going to produce one neuron, then one neuron, then one neuron, each one for every channel. Okay? But generally, what we want to do at the end is like, at the end, we're moving from one image to is there a is this a cat or a dog in this particular example? Okay, so we are moving from a 2D-dimensional word to binary question, yes or no, right? And I guess this is kind of why we connect the convolutions. At the end, we connect them to a classifier. So we're kind of moving from a set of 2-dimensional data into just a binary unit, yes or no, okay?
So is it correct to say that like the convolution is each application?
So question is it true to say that convolutions are good for extracting features and then classifiers, for instance, a neural network are actually useful for finding, classifying things? Yes and no, because actually you can do, so when you do image segmentation, what you do is basically you attribute every pixel of the image to maybe a label, chair, table, something else, right? So that's kind of a sort of classification that you're doing. But the thing is that you're moving from one image to another image where you put all the labels, okay? So in that case, I think you wouldn't pass through a neural network, because when you do the neural network, you kind of lose the spatial correlation of all the things. So it's kind of sensible to use a neural network now, because we are not interested in preserving the image. We're just interested in knowing if that image is a cat or a dog. I don't know if it makes sense.
Yeah.
Okay, cool.
So let's say your image has a 3 channel initially, and your kernel is like 3 times 3 times 3. Does that give you a 3-channel result? Or
So the question is, if I start with an image that, for instance, has 3 channels, for instance, red, blue, and green, and I use a 3x3 kernel, 3x3x3 kernel, does it give me 3 channels?
yeah.
No, it gives me 1 channel. So all these values get connected to this neuron. This gets connected to this neuron. This gets connected to this neuron. Okay, all these 27 pixels, 3x3x3, they get connected to this neuron. Okay, so each of these lines I'm drawing carries a weight. Okay, and what I do is I take this value, I scale it by this weight, and I add it into this box.
So adding all of
Yes, because this is still convolution. It's okay. No, it takes some time to kind of get your head around all this new terminology and things like that. But the idea is that I'm connecting everything to one box. And when then I move the kernel next, for instance, here, maybe, what I'm doing is I create a new block here, a new neuron, and I connect everything to this neuron. And then I slide it and I connect everything here. Okay, so if you think careful about this process, what I'm doing is stacking a row of neurons. Okay, then I take this kernel and I slide it down. So I'm going to start making columns now. And what I end up is just a flat sequence of neurons. So 1 channel. To get extra channels, to get an extra channel, you just need to choose a different set of weights here. Because these weights, these arrows, don't change value. Okay, they're fixed through all this sliding process. Yes?
Do we use the same kernel after we pull?
So sorry, can you repeat?
We use the same kernel after we pull.
So do we use the same kernels after performing the pooling process?
Yeah, because we yeah,
here, right? So we do convolution, then we do pooling, then convolution. Do we use the same kernels? No. We let the computer free to decide whatever is better now. So maybe the computer may put its efforts to kind of use the first kernels to identify small features, for instance, branches, for instance, leaves, and then in the next set of channels, maybe you could try to put these things together to think about bigger pictures. I don't know, a group of leaves all together and things like that. So no, the answer is no. And you can also see it by the fact that here we have 64 channels and here we have 32 channels. So here we're using 32 kernels. Here we're using 64 kernels. Okay, so we cannot keep using the same ones because we have more. Any other question? Okay, so if you want to come next Saturday, we're going to work on convolutional neural networks. Saturday at 11. It's in the room in front of this one. Yes, that one. Yeah, like PTSD. This weekend, this next Saturday. So we're going to probably work on some classification, and you will be able to see that it's fairly straightforward to implement a convolutional neural network. Now, what you usually do, for instance, if you're trying to classify images, is you usually take a convolutional neural network already trained by someone else. And so what we can do, for instance, is we can intercept the output of this process. So it's going to be kind of a block. Let's go to this picture. What we can do is that we can intercept this bit, maybe this bit, maybe this bit, and we can plug it into our own model. Okay. This is because convolutional networks are kind of tricky to train. You need to have a proper data set. They take a lot of disk space, so you need to be careful on that. So in many cases, these kernels that were maybe I don't know, trained to recognize cars, trucks, and buttons, they actually may be still useful to recognizing flowers from cats. Okay, maybe not entirely, but then you're going to add your own model here, and this is maybe kind of going to kind of help with classifying flowers from cats, for instance. We may go through this next time. I'm still not sure, but yeah, surely we will get the chance to implement a convolutional neural network using maybe smaller images and easier examples. But yeah, if you want, if you have any suggestion for these lectures, if there is something you wanted to be covered, then get in touch with me or with anyone else in the committee, but best if you get in touch with me. You can send me an email or send an email to data science. Okay? It's all right. I'm going to stop the recording now.